What's NBS? Anybody remember? I've seen this once before. It's N-bromosuccinimide. I don't care about that. You just need to recognize it as a reagent and realize that it is effectively equivalent to Br2. It is the compound that decomposes slowly and releases Br2 in the solution. It has solubility advantages because it's more soluble than bromine would be in most of these reaction conditions. NBS looks like that. And again, you don't need to know that, but you should know when you see NBS, it's the way of adding bromine to something conveniently in terms of solubility, and also making sure that there's never a lot of bromine around because it releases it slowly. And that's important here because you only want the monobromo product in this thing, and you don't want a multiple bromination to happen. And what you end up with is interesting. You end up with that compound. We keep the double bond. So this is not like the addition of Br2 to a double bond, even though that's what it would be. The fact that we shine light on it means it goes to a free radical mechanism. That means the bromine is going to break apart the Br dot. The Br dot's going to look for hydrogen to grab off the compound. And the most accessible, easiest to remove hydrogens on this compound are these. Those are referred to as allylic hydrogens. They are hydrogens on a carbon which is adjacent to a double bond. Those are even easier to remove than tertiary hydrogens. Why? Well, what do I get when I remove that? The intermediate that this reaction goes through would be that. And why is that a stable intermediate? It's a primary free radical. That shouldn't be terribly stable at all. What stabilizes this free radical? Back to the second lecture, which will go to word. Resonance. Resonance structure. Not very good at drawing this resonance structure, I learned last time. Drawing resonance structures with free radicals. But it's a resonance stabilized free radical, which moves the dot over there, which means it's the easiest hydrogen to pull off, and therefore that's the compound that you get. An allyl group, by the way, just in general terms, is anything that has this carbon attached to a double bonded carbon. It could be other things attached on both sides of that, but that particular group within the molecule is called an allyl group. This is a very useful reaction, especially in terms of synthesis, because it's a way of putting a bromine in a specific place in a molecule, and that already has a double bond in it, without breaking the double bond. So that when you're finished, you have a bromine somewhere, but you still have a double bond, so you can do further chemistry after that. If you just add HBr to this, you will put a bromine on there, but you'll end up with the double bond gone at that point, and therefore doing anything else with that compound is difficult. So, for example, here's an example I made up. If you start with cyclohexene and added NBS and shine some light on that to get things started and make the free radical, what you end up with is the allylic bromide, bromine which is adjacent to to the double bond. And at this point, you can do lots of other things with that because you still have a double bond, so you can do any double bond reaction that you have in order to continue your synthesis. If, for example, I wanted to make that, what could I add to my bromide? Bromide into a double bond. First reaction we looked at when we talked about chapter 8, 7, whatever the heck it was, alkene reactions. Any kind of strong base will eliminate an H to the R from a molecule and put a double bond in. Clean, one step. More reactions in this chapter, actually 5 more. 3 of them are all related to one another. Mechanisms you don't have to know for now. The mechanisms are in the next chapter, which we'll come back to. But another way to make alkyl halides is to start with an alcohol and turn the alcohol into an alkyl halide. That's mostly the chemistry that you're going to deal with next semester when you talk about the chemistry of alcohols. But in terms of doing synthesis, these are good reactions to know. And so he introduces you to 3 of them. If you start with a tertiary alcohol, the easiest way to convert this into an alkyl halide is just to take your tertiary alcohol and react it with the halogen directly in the gas form. That is, take the halogen and bubble either the chlorine gas or bromine gas through your solution. And the solution can be cold. This is a reaction that happens rapidly. It's a reaction that gives very good yield. And what you end up with is the halide, the halogen replacing the OH and water. So it's a fast, very good, very effective reaction, but it only works with tertiary alcohol, for reasons that we'll see in the next chapter. If you have a primary or a secondary alcohol, however, you're not out of luck. There are ways of turning these into halides. You can take a primary or a secondary alcohol, and if you want the bromide, react your alcohol, either primary or secondary, with phosphorus tribromide, PBr3, and that will give you that and a bunch of other inorganic stuff. Or you can take your primary or secondary alcohol and react it with thionyl chloride. That's a double bond on the sulfur with 2 chlorines, so it's like an acetone molecule where sulfur is the central atom instead of carbon. And what you end up with is the chlorine replacing the OH. The advantage of these reactions is that they give good yields. They can be run under fairly mild conditions. so that if there are other functional groups inside the molecule, they tend not to be interfered with. So it's a very good way of turning an OH group into a halogen. This is one of the ways you can finish that synthesis, which I erased, I think, where you ended up making the alcohol with the anti-Markovnikov addition to put the OH where you wanted, and then you could have reacted that with PBr3 and replaced that OH with a bromine, and end up with the anti-Markovnikov bromide without having to use the peroxide reaction. The mechanisms for